Hello everyone, and a warm welcome to SPI Laser's webinar on nanosecond pulsed laser welding. My name is Mike Poulter, and for those of you who don't know me, I'm Product Manager here at SPI Lasers, and today I'd like to talk to you about nanosecond pulsed laser welding as a new approach to joining thin section similar and dissimilar metals. Please feel free to submit questions during the webinar using the chat function, and I'll try to address these at the end of the presentation. Here's what I'd like to cover in the next 45 minutes or so. I'll start with a short introduction on SPI as a company. I promise this will be short, as I'm aware many of you will know of us already. Then I'll go on to highlight some key target applications for the new process, the nanosecond welding process, and discuss the challenges associated with using traditional laser welding methods. I'll then move on to talk about important characteristics of SPI nanosecond pulsed fiber lasers and the benefits that they provide over conventional laser welding for these particular applications. This will lead us nicely into the detail behind the nanosecond joining process, which includes the metallurgy of the joints, joint configuration and welding geometry, physical processes of the nanosecond welded joints, and then go on to talk about examples of similar metal combinations and dissimilar metal combinations. So just to start with a brief company overview, SPI Lasers is based in the UK, and we have a core competence which is in research, development, manufacture and service of optical fibers and fiber laser technology. In addition to this, we also have significant expertise in the development of laser materials processing with applications laboratories sited across the globe. This enables us to provide our customers with innovative laser processing solutions to implement at the system level. The nanosecond pulsed laser welding process is just one example of this. So that takes us on to the key application areas for the nanosecond welding process itself. Where is it used at the moment? And it is used already. This is a process that has been developed by SPI here, and it is being used in industry already. There are thousands of lasers already deployed for this application, and it is used across the board, for example, in surgical medical devices and the production of consumer electronics and the packaging of, and also something which is actually up and coming, and I'm sure you guys are aware of this, the production of batteries and energy storage solutions, particularly around the processing and welding of battery foils, both the anode and cathode tab terminations, also at the higher level manufacturing of batteries around bus bars, plates and power distribution. And it also includes sensors and gauges, amongst other things. More largely, it's being used within electric mobility, particularly in the production of electric cars and electric vehicles. Just to discuss that a little bit further and put context onto the process itself, this is an example of where the welds are being implemented, or at least being considered for implementation for e-mobility. There are welds within the electric motor, the transmission unit, power electronics, within the battery packs, the cells, and also the battery packs themselves, and the packaging of those batteries, the charging, and also the transmission lines. All of these applications are being used, lasers are being used for these applications right now. However, there are some challenges to traditional laser welding in these applications. There are a number of different laser types being used for laser welding today. We have CW, modulated CW, QCW, and pulse lasers with long, high energy, low frequency pulses, for example, lamp pump solid state lasers. Compared to these sources, nanosecond pulse lasers tend to have lower average powers and pulse energies, which has historically restricted their use in welding applications. However, the challenges are well known with these conventional laser welding processes, particularly the control of heat input and the resulting heat affected zone, the price versus performance, how cost effective the solution is for a given application, the quality and repeatability of the process itself, and the flexibility of the laser in doing multiple different joining processes, and of course the joining of dissimilar materials. So the question really is, how can we use nanosecond pulse laser sources to address these issues? And that's what I'd like to cover in the webinar today. In very basic terms, if we compare the output of a nanosecond fiber laser to a traditional lamp pump solid-state laser, for example, we see that the difference really is in the method by which the energy is delivered in time. For a nanosecond fiber laser, the same energy can be delivered, but in shorter, more frequent increments. The new nanosecond welding process obviously won't replace many of these methods that I previously discussed and many of these sources, but it has benefits for certain applications, particularly around the joining of thin section metals, as different pulsing regimes, these different pulsing regimes that you see on your screen, affect the materials in very different ways. I'll go on to talk about that in more detail. Here, the nanosecond pulse laser can be shown to be more cost effective than traditional methods, using less average power and therefore fewer pumps to do the same work, or indeed, alternatively, to do more work for the same average power. So this brings me on to talk about the important properties and characteristics of the SPI nanosecond fiber lasers and why these are beneficial to the process itself. Nanosecond pulse fiber lasers from SPI is the Red Energy G4 range. We offer these products from 20 watts to 250 watts average power. However, they deliver peak powers in excess of 10 kilowatts, sometimes up to 50 kilowatts, depending on the beam quality. Pulse energies range from 1 millijoules up to 5 millijoules, which is significantly lower than traditional methods, traditional sources used for welding, the CW, the QCW, and the large lamp pump sources. However, these lasers, the Red Energy G4 lasers, will deliver nanosecond pulses from about 3 nanoseconds up to 2,000 nanoseconds, that's 2 microseconds, and also at pulse repetition frequencies from 1 kilohertz up to 4 megahertz. There is a selection of mode profiles available and beam qualities with M squared between diffraction limited of 1 and 5 times diffraction limited, M squared 5. This is already a proven industrial tool used in their thousands throughout industry, easily integrated and compact, and are used in a number of other applications, mainly around marking and ablation, engraving and cutting. But now we're employing them for welding applications. Important to the Red Energy G4 is the ability to select individual waveforms. These are pulse durations, pulse shapes in time. Waveforms offer users of the pulse nanosecond lasers with many different options, operating orders of magnitude control in nanosecond pulse duration, up to tens of kilowatts peak power, hundreds of kilohertz pulse repetition frequency, as I say, in some cases up to 4 megahertz. These lasers are significantly differentiated from the other laser sources, where characteristics like peak power can be maintained even at high PRF for these nanosecond lasers. This ability to tailor the delivery of the input, the energy input in time, and in particular a short duration of time, is key to their use as a tool for this joining process. This is a little more detail around the options associated with beam quality. This adds to the flexibility of the nanosecond fiber laser sources, as there are options for different beam quality and associated maximum pulse energy. This provides just another level, another lever to pull when optimizing for a given weld. I'll go into that in a little bit more detail later. So the question on everyone's lips, I'm sure, is why use nanosecond fiber lasers for welding applications, and what are the benefits over the conventional welding sources? When bonding thin material in particular here, there's a requirement for reliable joining process that avoids overpenetration, distortion, and warping of the material. In conventional keyhole welding processes, for example, overcoming material thresholds requires relatively high powers, usually around 200 watts average power, for example. The challenge is actually even greater when you're joining bright metals, that is reflective metals, as you need to overcome the reflectivity and the thermal conductivity. The solution that the nanosecond laser offers is to control, really precise control of the heat input by an alternative mechanism for energy delivery. If we look in a little bit more detail into the statement I've just made, if we look at classic laser welding, this is CW laser welding, conduction limited, on the left, which shows the high width to depth ratio. On the right, there's traditional keyhole welding. This will be familiar to a lot of people around for traditional laser welding of CW or QCW lasers. This shows the high depth to width ratio that you'd achieve there. If we now compare these to the nanosecond welding process, just to try to illustrate that it is very different here. This is a picture of a micro keyhole weld using a CW laser running at 5 millimeters per second weld speed. If we compare that to the nanosecond process, the new nanosecond process, we have a much different mechanism here. You can see that the nanosecond process is not characteristic at all of a normal CW weld, for example. It's much more like an electron beam weld in its cross section, which is shown here. And what's really interesting between these two images, or three images, is that these are all taking at the same average power. So the same average power for the nanosecond pulse laser on the right compared to the CW laser on the left shows a very different mechanism that we're using here at the micro level. Joining dissimilar metals has long been a challenge for welding and design engineers. It's a combination of physical properties and metallurgical incompatibility that governs the weldability. However, there are a lot of potential applications that require such joints, particularly bright metals and steels and aluminium alloys, for example. Fundamentally, fusion welding of dissimilar metals creates problems associated with the formation of brittle intermetallic phases. These can form planes of weaknesses, making the joints susceptible to fracture. These intermetallics typically manifest themselves at the interface of the weld pool and form based on time and temperature of the weld itself. It's the heat input that's a key factor of their performance here. And what we offer by this new nanosecond weld process is a process which is actually not based on a large weld pool. Just to highlight this further, this is an example, a table using a lamp pumped ND-YAG laser, so a lamp pump solid state laser. This is a traditional method of laser welding, showing the compatibility of welding dissimilar metals. You can see here where B being bad, A acceptable, G is good. There are a huge combination which are just really very difficult to achieve using the traditional longer pulse methods. You can see, for example, molybdenum, you can see is very difficult to weld to most of the materials other than itself. So why is it that the nanosecond pulse laser is good at overcoming these issues? By using a complex interaction of multiple process variables to control the heat input, and this is the key here, this is all about controllability of the heat input itself. And also on top of that, using other variables such as scan speed, beam quality, pulse duration, pulse frequency, and pulse shape we're able to overcome some of these issues. By spatial and temporal interaction of the pulses with high peak powers, we're enabling this is further characterized by the pulse tune waveforms. This provides control over the pulse duration and all of the other characteristics in time of the laser pulses itself. This is also refined through the geometry of the weld itself, as defined by the scanner. I'll go into that in a little bit more detail further on into the webinar. Ultimately, what does this achieve? It allows us to replace common joins that are normally done with adhesives, stakes, rivets, pins, and screw-type fixtures, and even soldering and brazing in some instances. And what is key to this process is it still provides electrical conductivity and with good thermal dissipation. So let's now move on to the process itself. I think this is probably what is of most interest on this webinar, and discuss what it is that's different with the nanosecond process compared to traditional at the metallurgical level. As I said earlier, what is absolutely key to this is the delivery, the controlled delivery of heat input. And the reason why we want to do that is we're trying to prevent large-scale weld pools, and therefore this intermetallic zone that you see on traditional welding. This is an example. This picture is an example of a 0.8 millimeter diameter spot weld, which can be achieved through 150 microns of copper onto 400 microns of aluminium in this case. And it's done in under 300 milliseconds. The process time is quite quick. It's done using a red energy 70 watt EPZ laser from SPI. And the metallurgy here is very interesting, as these spot welds don't show the same characteristics as a conventional spot weld. There is still a distinct single weld nugget, and there's still separation between the two metals themselves. Actually, it's a mechanical joint rather than a metallurgical joint. What we're seeing here is a mixture of metal, but not at the molecular level. What is happening is we're actually drilling through the top copper layer into the aluminium, which then melts and then flows back up through the copper, creating a mechanical bond. You can see there are some this yellow discoloration at the top around this area here. It's possible that these are the alloyed intermetallics that are forming, but there's very limited amount of this, and the idea is to try and make this as minimum as possible. So staying with copper to aluminium, this is an example of using a 70 watt HSH laser for doing the same application. This is a really intriguing cross section. What we're showing here is a cross section whereby, again, we've effectively drilled through or cut through the copper layer, created a melt pool in the aluminium below, and you can actually see, probably by capillary action, the flow of aluminium up through the cut, which is creating almost a rivet-like structure in the joint. This is really innovative. It's something that you can see. You're not seeing any alloying, no intermetallic zone, and it really is a mechanical bond here. What's interesting, though, however, is this process actually differs depending on the materials that are used, and indeed the order of the materials, which one is on top. For example, here are some more examples. On the top left, you have copper and aluminium, as you've seen in the previous slides. But also on the right of that, you see aluminium to copper. So this is reversed, and you can actually see there's a very different structure here. Whereas the one on the right, the one on the left shows flow of aluminium up through the copper itself. The one on the right is actually more like a staking process, where you're actually producing, pushing material from above into the material below. This varies very differently between the materials used and, as I say, which order they're in. We have stainless steel to aluminium, and even difficult combinations like titanium to copper on the bottom right there. Just looking at this in a little bit more detail, this is an SEM image, and subsequent EDX analysis of a section join. This is again looking at aluminium to copper. What this is basically showing is that although we do again have a mixing of the metals itself, you're almost stirring metallic metal up rather than metallurgically bonding them into an alloy, into an intermetallic zone here. There are no alloys formed, therefore it's overcoming some of the challenges associated with traditional laser welding. Here's another example of an EDX for copper to stainless steel. Again, you can show on the image, particularly on the right, you can see that the copper on top onto the stainless on bottom, there is a distinctive mix of the metals, but again, no change in the metallurgy itself. You still just have copper there and stainless, but they exist in the different layers. You can see here that as it's mixing, it's creating this mechanical bond. Some people have referred to this as almost like raspberry ripple ice cream, where you are mixing the two liquid metals at the time, and then solidifying, but not actually mixing it at a molecular level. Here's a final example of brass, for example, to stainless steel, showing the same thing. You can see here where brass on top, stainless steel on the bottom. Again, although we're seeing mixing, effectively stirring of molten metal, which is then solidifying, you're not actually seeing any alloys forming within the joint. This is an interesting quote that we received from the Welding Institute. This is after we asked them to have a look at the cross sections of these joints, and they give us this feedback. Effectively, from the images taken, they believe that there are no intermetallic compounds being formed. If they are, they're not easily observable at all, and they are in clearly defined regions, not in clearly defined regions. This differs from other methods of dissimilar metal joining that they've seen previously, including even stake welding that they produced with the CW laser at the same wavelength of 1 micron. And importantly here, and this is the key statement, within the metallic phase formation, there's clearly a temperature and a time dependency that contributes to the phases formed and indeed their size. What we believe is happening here is that there is actually minimal time effect in these joints because of the fact that we're using nanosecond pulses. That prevents these phases from being formed, that produce these intermetallic alloys. This makes them interesting and indeed, we believe, novel. So now that we've talked about the metallurgy of the process itself, we can go a step further and talk about joint configuration and indeed how we might optimize the welding geometry itself to try to optimize different characteristics of the join. So now we're talking about, or we're starting to introduce the principle of actually how we scan the laser using a galvanometer scanner over the surface of the material rather than the laser characteristics in time itself. There are a number of methods we use here. We often employ a spiral. We can also use a single line with a wobble rastered in a linear direction. We can also use different other architectures such as cross hatching, single line hatching, or dashed lines, depending on what we're trying to achieve. I'll go on to this in a little bit more detail. So here we have some examples of the main welding geometries that we use with nanosecond pulse welding. Each geometry has its own particular benefits. For example, spiral geometry is best used for spot welding. We use parallel lines because they're great in terms of joint strength and have very little or no heat affected zone. We use cross-hatching where we want to join or weld large areas, and single wobble line welding can be used for both seam or butt welding, and provides good or excellent heat management. So it really depends on what you're trying to do, which governs the welding geometry itself. Here are some examples of cross-hatching, of large area cross-hatching, where we've effectively we've employed this on multiple materials. For example, aluminium to brass, copper to stainless, aluminium to copper, stainless to aluminium, stainless to copper, and even titanium to aluminium. This is showing we could create 4mm diameter weld sections in around about 1 second process time. So it's pretty quick process. Alternatively, we can use spiral geometry. So given the fact that we have a spot size, which is, for spot welds at least, a laser beam spot size of around 50 microns, we need to use different techniques to increase that area for the weld itself. And we would do this through the creation of things like these spirals. We use this spiral path, and not only that, we can not only change the characteristics of the laser beam, the laser pulse, the peak power, the pulse repetition frequency, but we now have another set of parameters that we have to control to optimize the weld. For example, the radius is associated with the spiral, the inner radius, the outer radius, the ramp that we have in terms of pulse repetition frequency and speed going in and out of the spiral, in terms of rise time, and also indeed the overlap of the individual nanosecond pulses. All of these things can be used as levers to optimize the given weld process. And we have at SPI come up with a number of recipes which are optimized for any given combination of material or thickness. What does this mean? This means that we can actually open up the possibilities for design at the macro level on the weld. We can then design, for example, for optimized electrical conductivity. We could optimize for the maximum pulse strength, penetration, or nugget shape. The available space might be a commodity, so we might want to optimize for that. Importantly, we also have to consider the heat input and any heat affected zones or witness marks that may or may not be desired. This is an example of where we've created an S-type structure. This is to increase the peel strength in one particular direction of a weld, just illustrating again that different geometries can be used in combination with the spot weld, which has already been optimized for given laser parameters for the materials being used, in order to optimize the macro properties of the weld itself. This is an example, a practical example of what we're being asked to do right now with this process. It's around battery cell manufacturing, and the requirement here is to weld, for example, copper or aluminium tabs to battery cells which have already been produced. In this case, we're using a galvo scanner with a 100-watt EPZ laser, and actually requires basic fixturing. What is important here is the contact between the tab itself and the battery. Once you've ensured that, then the weld is pretty straightforward. Sometimes shielding gas is required. This is just to prevent oxidization in some cases, and can be used to make the weld look cosmetically, improve the cosmetic look of the weld. The objective in this case for this particular application is to produce strong welds with no burn through or witness marks. The key requirement is effectively for end users are looking to have a process that is more tolerant to key parameters such as standoff or spot size. We are looking here to not produce anything particularly beneath the tab itself in terms of a heat affected zone. What's not obvious from the outset is how you would do that in terms of spot geometry, in terms of the weld geometry itself. Instinctively, you would just create a larger spot, a larger spiral. It turns out actually that in most cases, this isn't the optimum way of doing things. And in fact, creating smaller spots and multiple smaller spots with the same area is actually the preferred way to go. The process time for this is very similar, but you get improved peel strength and tensile strength using this method. Also, there are no witness marks on the other side of the weld of the joint. The reason why this is because this is all about, the criticality here is all about control of the heat input itself, and by separating the spot into smaller spots, we are just again we're allowing us to control that heat input that little bit better. This is a picture of the industrial process itself being employed on 18650 batteries and battery tabs. This is producing both the anode and the cathode weld, 0.15 aluminium to 0.4 millimeter stainless steel in this case. And the guys who have qualified this did over 100 cross sections of the weld, which showed no punch through and no heat affected zone on the other side of the tab. What's interesting is that actually the same laser they're employing to do the cutting of the contact sheet itself. So this laser, this nanosecond pulse laser, is not only being used for the weld, but it's also being used in a multi-process application to cut out the sheet, the contact sheet itself. So where do we go from here? Obviously, as we develop new products and we feed back the knowledge from this application into product development, we're looking at moving to higher average powers on our nanosecond pulse fiber lasers, and we've been doing some investigations into what that means from a process standpoint. This is an application again around batteries, where we are welding 0.15 millimeter aluminium foil to a battery cell. We're finding actually that we're now getting huge benefits in productivity at higher average power with reduced overall heating. In fact, for a 3 times increase, or roughly 3 times increase in average power from 70 watts to 200 watts, we're seeing a 6 times increase in the speed. So a reduction, 6 times increase, 6 times reduction in the time per spot, and a halving of the overall energy for a given spot or for a given weld. The reason why we think this is happening is because there is residual heat that is still left over at higher average powers, which is actually benefiting the process at the nanosecond level. This is another example of using the new 200 watt EPZ nanosecond pulse fiber laser, going through not just thicker materials, but also multi-layer materials. Not just multi-layer, but different materials. In this case, we're looking at aluminium alloys and nickel-plated copper. Again, this is for largely battery applications, but it just shows the flexibility that you can get from this process. So the next question is, what are the physical properties of the nanosecond welded joints now that we've created them? Here are some examples of tensile strength measurements that we've made on spot welds. Again, this is using that spiral process with copper to copper, copper to brass, bronze to bronze, so similar metals, and also on dissimilar metals, copper to aluminium and copper to brass. This is showing the tensile yield of those spot welds. In many cases, you actually see, because obviously this is really focused for thin section metals, the weld is stronger than the actual section metal itself, and the metal will yield before the weld will, leaving a nugget behind. This is an example of copper on aluminium. There are other interesting phenomena which are happening. This is an example of where we tried a post-process cosmetic pass. So once the weld had actually been done again, this is a spiral spot weld. Once it had been completed, we tried a post-process cosmetic pass just to improve the look of the weld itself. What we actually found, though, is that in some cases, not all cases, but in some cases, this actually increased the strength of the weld also. In this case, for copper to aluminium, the joint strength increased from 116 newtons to 240 newtons. That's 85% increase in weld strength just by doing a pass. We believe that's just due to a remelt of the material on the surface of the top copper surface layer. So now I can take you on to some examples of the nanosecond joining process, and we'll start with some similar metal combinations. This is an example of stainless steel to stainless steel welding using the nanosecond welding process. This is actually how we first found out about this process in itself, and indeed stumbled across it here at SPI through our applications development. We found that actually when we're trying to weld, it's usually believed that you need a lot more pulse energy and higher peak power, more average power in order to weld particularly thicker materials. But we actually found that for a nanosecond pulse laser, sometimes the opposite is true. What you actually see here on the left is a 70-watt laser at maximum pulse energy, at maximum peak power. And what we're actually seeing is lots of oxidization. It's almost starting to cut through the material itself. However, what you then do if you then back off on the pulse energy and indeed the peak power and optimize the duty cycle so that you deliver the heat input and you really control that heat input, then you start to get a better weld. And in fact, by the time you get to this image on the right, where we have optimized both the pulse energy, the peak power, and indeed the duty cycle, we come up with what is rather a nice looking weld, which has pretty good quality in terms of strength and other properties. This is the same weld. For example, the 150 micron sheets lap welded together, again stainless steel to stainless steel, showing the top, the bottom of the weld in this case, and its deformation under peel. We actually find that the material itself gives up before the weld does. We had similar results achieved in thicker sheets, up to 250 micron, which was at 50% of the welding speed in this case. Looking at, again, the metallurgy of this particular weld, this is the stainless steel to stainless steel weld. We can see a number of things here. The observations are that we actually have good penetration into the lower material from the upper material. We really can control the depth of the weld itself. You can see almost where we've been able to control each individual part of that weld as we have used the spiral geometry through the top into the bottom layer. The process parameters here, we're again using 70-watt laser with a standard scan lens in a spiral mode, running at 50 millimeters per second scan speed. There's little or no change in the surface height on the top, and no gap between the two layers. Also, what you'll see here is there are absolutely no witness marks, no heat affected zone on the bottom of the joint. The tests completed on this in terms of appeal strength yielded some really good results. For two 1 mm welds in a 0.5 mm lap, yielded over 1,000 newtons in terms of appeal strength, and we're seeing some really good results across the board, not just within stainless steel, but other similar metals. So if we move on now to some examples of dissimilar metal combinations, which is of some real interest at the moment in the industry. This comes with its additional challenges. Obviously, we have some metals with particularly high reflectivity. We've already talked and discussed about the dissimilar metallurgy that occurs between dissimilar metals, having different melting temperatures, also different cooling rates. We also have coatings, platings, and other oxide layers that exist on common materials, metallic materials. So the object here really is to create mechanical joints independent of all of these things using a nanosecond near-infrared laser. Here are some particular examples, again using the spiral method of spot welding. In this case, we're joining stainless steel, copper, aluminium, and brass to stainless steel. In red, you can see the process time. This is the full process time for all 9 spot welds, not just per spot weld, and the tensile yield test for each of these welds. Again, down the left-hand side here, you can see the common parameters which were used during the process, just for reference. I have a video now of welding copper to stainless. Now you can see while we're doing this, we are creating these spot welds in a particular order. This again is another parameter that we're using to control the heat input into the weld itself. Moving on to joining to aluminium, again, taking stainless steel, aluminium itself, brass, and joining all of those together, and copper also. Again, down the left, you see, for reference, the kind of parameters that we're using for this particular application. And again, with the process times and the tensile strengths, tensile yields in red there, you can see that some of them are in excess of 1,000 newtons. Previously, we've seen over 3,000 newtons for some welding combinations, and indeed we're unable to break some of them given the equipment that we had available to us for testing yield and strength. This is another example of aluminium to stainless steel. What you'll notice about this one is it's very much quicker than the last one. Again, we're using all of the parameters to tailor the joint itself, but there is less need in this particular case to control the overall heat input in the top surface, which means that it can actually be done much more quickly compared to, for example, the previous copper example, where copper was the top material. If we are now joining to copper on the bottom, where we take, for example, stainless, aluminium, and brass again, joining to copper on the bottom, again, these are the kind of process parameters used. We're talking about now process times that can really vary quite a lot. You can go from around 5 seconds in some cases up to 20 seconds in others, depending on the combination used. Again, with pretty impressive tensile strength. This is an example of the stainless to copper video. Again, this is quite a rapid process. This is a particular combination where we can go quite quick over this process. Typically, the top ribbon that we're welding to here is around about 150 microns to 300 microns. Finally, we can talk about joining to brass, for example, again using the same materials, stainless, aluminium, and copper, and reporting on the same information there. I can show you a video of this. This is an intriguing video. You'll notice actually at the very end we do a cosmetic pass. You can see to cover the welds. That's again just to make the welds look a little bit nicer, but also can, as I said earlier, in some certain combinations can add to the strength of the weld itself. So this is just the start of the story in terms of what we're doing with nanosecond joining. I mentioned molybdenum earlier as an example of a particularly difficult metal to join to other metals. This is an example where we've welded aluminium to molybdenum with no problems using this new nanosecond welding process. So in summary, really we're looking at all different types of combination of metals, and we've really just scratched the surface of what we think this process can do. And in fact, to date, of all the different combinations that we've tried, we've managed to successfully join and weld all of them together. This is a table of all the combinations that we've tried to date internally, and we obviously have a lot more to investigate. But we believe that there's a lot more to come in terms of what this process can offer for particularly dissimilar metal welding. This process has been patented by us at SPI Lasers. However, licenses will be provided with the purchase of all nanosecond pulse fiber lasers from SPI. So in summary, nanosecond pulse welding offers a novel solution to joining thin section metals and actually provides a multi-process capability whereby you can also cut and mark, for example, at the same time within a manufacturing process. The process mechanism itself is significantly different compared to traditional welding process and is suited in particular to thin section metals. This is enabled through the enhanced control of thermal input from the nanosecond pulse fiber laser, and it's also further tailored by beam quality options to offer the right tool for the job. If you require more pulse energy, we can offer that through a higher M² beam quality option. Further flexibility in the process is provided through a wide range of pulse tune waveforms, and also in combination with scanning techniques that have been discussed. In doing all of this, we have new opportunities and possibilities for joint design, optimizing for particular properties of the joint, whether it be thermal conductivity, electrical conductivity, or indeed strength. This process offers new potential in welding, and in particular for dissimilar metals. Well, thank you very much for your attention. I'll take some questions now. Let me scan through some of the questions that have been submitted. Okay, so this is an interesting one. I have an interesting question here. Someone has noticed on the SEM images that it looked like there was some porosity in the welds in the joints, and that is indeed correct. Absolutely, there is some low level of porosity when we do this nanosecond welding process. However, that can be minimized through optimization. Again, we have so many levers to control this process through pulse duration, pulse energy, peak power, duty cycle, beam quality, and indeed then the welding process through the spiral, the geometry of the spiral. All of these things can be optimized to minimize the porosity of the weld in order to try to optimize. But at the end of the day, you have to ask yourself, is the joint fit for the purpose you're trying to achieve? In many cases, we believe it is. We are selling thousands of lasers at the moment into these applications, particularly in consumer electronics and battery processing. So in many cases, we believe that although, yes, there will be some low-level porosity, for many cases, this is still fit for purpose. Looking at a different question here, someone's asking, how thick can you weld? So as I say, this is really for thin section metals. What do we mean by thin section? To define that in a little bit more detail, we're looking at in terms of bright metals like copper. We will go up to around about 0.5 millimeter in section, up to about 1 millimeter for some other materials such as aluminium and stainless steel. If I extend that, extend that question in the opposite direction and say how thin can you go also, we are welding thin foils down as thin as 10 microns to solid plates using this nanosecond welding process. Let's see if I can find one or two more questions here. Okay, there's a question here on hermetic sealing. Can we use these welds to create hermetic seals? There is no reason why not, particularly for the single line wobble welding, seam welding technique. As long as, notwithstanding my previous comments on minimizing porosity, there's no reason why this particular process shouldn't be usable for hermetic sealing in relevant applications. Although we haven't used that and employed that to date, theory states that it should be possible. I'm looking at a final question here, asking a little bit more about the aesthetics of the weld and what we can do to improve the cosmetics of the weld itself. As I say, in some circumstances, it's useful to do a post-processing cosmetic pass, usually with a shorter, lower energy pulse to cover the welds themselves. That usually neatens the weld up a little bit and can also, as I said earlier, increase the strength of the weld itself. What we're also finding is that using assist gases can also help. Argon in some cases can reduce the presence of oxides and increase the make that weld look a little bit more aesthetically pleasing. So I think I'm running out of time, so I'll leave that there. Just a final word. We have some more webinars coming up in June and September, so later on this year, on oscillation welding and also on the new vary mode feature on our CW lasers. So please tune into those. That's enough for me. Thank you very much and happy welding.